Welcome, computer engineering students. So today we're going to dive deep into this explainer to really demystify the exact mechanics of input and output interfacing using assembly language. Because let's be real, if you've ever wondered how the code you write actually pushes electrical signals out into the physical world, well, you are absolutely in the right place.
Think about the actual physical components out there, the circuit boards, the capacitors, the resistors. Our main goal today is to bridge that massive gap between software and hardware. We really want to understand the low-level hardware signaling that lets your microprocessor actually talk to this physical reality.
Okay, let's quickly hit our roadmap. We're going to start with an introduction to I/O operations, move into the in and out instructions, explore fixed port and variable port addressing, map our assembly operations to actual signals, and finally wrap up with emulators and real-world hardware.
Welcome to I/O operations, bridging the CPU and external devices.
We have to start by defining the fundamental problem here, right? An isolated CPU is essentially useless unless it can actually connect to external devices, like your keyboards or screens. So every microprocessor, by absolute necessity, provides specific I/O instructions to establish this vital communication link with the outside world. Literally, it's the only way data gets in and the only way results get out.
Section 2. The in and out instructions. The accumulator as a loading dock. Now, let's explore the core commands that essentially act as the shipping doors for our data flow. We've got two primary instructions here, in and out. The in instruction reads a byte or a word from a provided port directly into the accumulator. The out instruction, it does the exact reverse. It sends a byte or word from the accumulator out to a provided port. For example, an in instruction might pull a keystroke from a keyboard controller right into the accumulator, while an out instruction might push a command byte to, say, spin up a cooling fan. The absolutely crucial takeaway here is that the accumulator acts as the microprocessor's central loading dock for all incoming and outgoing data bytes or words. I mean, everything flows through it.
Section 3. Fixed Port Addressing Explained, the 8-bit immediate approach.
Let's look at how this builds our first addressing method. This is where the port number is just hard-coded right into the instruction syntax. We call this fixed port addressing. It allows data transfer using an 8-bit I/O port address. And it's called fixed because that 8-bit port number is completely immutable. It's attached directly to the opcode, just like immediate addressing. Once you compile it, boom, that port is set in stone.
So let's think about the actual hardware translation for an instruction like INAL6AH. What is actually happening down on the silicon? Well, data from I/O address 6AH is designated to be input to the AL register. But wait, the address bus is 16 bits wide, so the microprocessor automatically zero extends that 8-bit port address. The 6AH becomes the 16-bit address 006AH. Finally, this full 16-bit address is physically pushed across pins A0 through A15 on the address bus. And that, right there, is exactly how the hardware routes your 8-bit software command.
But as engineers, we have to ask the next logical question, right? What if you need your I/O port destination to dynamically change while your program is actually running? This brings up a critical, real-world engineering challenge: dynamic port allocation during program execution.
Section 4. Variable Port Addressing Explained, utilizing the DX register.
To solve that dynamic challenge, we turn to variable port addressing. Instead of hard-coding the port, variable port addressing allows data transfers using a full 16-bit port address that is safely stored inside the DX register. Because it's stored in a register, your program can actually change or vary the destination port on the fly during execution just by updating what's inside DX. Imagine you have an array of identical temperature sensors on consecutive ports. You can load the first address into DX, read it, increment the DX register, and loop. That is something that's literally impossible to do with fixed ports. And this brilliantly illustrates the architectural difference we face when writing our code. Fixed port addressing is hard-coded, sits right next to the opcode, and is strictly limited to an 8-bit number that has to be zero extended. On the flip side, variable port addressing is entirely dynamic, utilizing the full 16-bit capacity native to the DX register.
Section 5. Assembly Operations and Signals, Mapping Software to Hardware.
So when you write these instructions, how do they translate to actual physical electrical signals on the motherboard? Well, think about the execution of the instruction OUT19H, AX. The contents of the AX register are firing squarely across the D0 to D15 data bus. Meanwhile, the fixed address, which has been 0 extended to 0019H, is targeting pins A0 to A15 on the address bus. And crucially, this is all accompanied by an active low IOWC, or Input-Output Write Command Port Control signal. That right there is your software manifesting as raw electricity.
To prevent cognitive overload as we design our systems, this strict breakdown table from our source material shows the exact syntax options we have available. Notice exactly how the AL register handles 8-bit operations. See how the AX register handles 16-bit operations, and even EAX for 32-bit operations. You can see precisely how they interact with either the fixed 8-bit ports, which are labeled as P8, versus utilizing that 16-bit DX register. Honestly, think of this breakdown as your foundational blueprint for moving data around.
Section 6. Emulators and real-world hardware. Testing your code. Implementing these assembly instructions directly on physical I/O devices immediately can be incredibly difficult, and honestly, it's highly prone to causing short circuits if you accidentally write to the wrong address. Nobody wants to fry their board, right? That's exactly why we use emulators. Emulators provide a simulated sandbox, allowing us to safely verify and debug your assembly code before you ever even touch the actual hardware.
Now, these software emulators offer 7 highly specific virtual devices for us to test against. You can simulate traffic lights, a stepper motor, an LED display, a thermometer, a printer, an actual robot, or just a simple test device. This incredible setup allows you to visually confirm that your in and out logic is driving a simulated robot arm or spinning a stepper motor correctly before you run the risk of breaking some really expensive lab equipment.
However, you will eventually have to leave the sandbox. When moving from the emulator to reality, remember that while generally any x86 family CPU can control these devices, there are always hardware quirks. Differences in the base I/O port numbers between different CPU models might actually require you to use some tricky electronic equipment to alter the connections and make your tested code interface properly with the real board.
Finally, once your code is perfectly tested and verified, we have this exact 4-step process for taking it live. First, you take your compiled binary, the .bin file, and physically write it into a read-only memory or ROM chip. Second, upon boot, the microprocessor system reads your program directly from that ROM chip. Third, the system loads that program into the much faster RAM module. And fourth, the system finally executes your code, sending your I and out signals dancing across the physical buses.
As you step into the engineering lab today to apply everything you've just learned in this explainer, I really want you to carefully consider your design choices. When you sit down to architect your next assembly program, will you lock your hardware pathways down permanently with fixed ports for simplicity, or will you unleash the runtime flexibility of the DX register to build a truly dynamic system? The choice is entirely yours. Keep building, keep testing, and I'll catch you next time.